Good morning, everyone. Thank you so much for joining us for the Earth Week panel on geoengineering. Thank you so much for joining us for what I know will be an exciting discussion on geoengineering, which, as I'm sure you know, is a topic filled with exciting future-forward technologies, but also fraught with ethical questions and controversies. I'm honored to be joining my esteemed panelists today, though I don't come from engineering or science, but from the theater department, where I work with the theater director, Brian Brophy, on a project called Mach 33, the Caltech Festival of New Science-Driven Plays. After we've selected the plays for our festival, we connect our playwrights with Caltech and JPL science mentors to help the playwrights develop the science in their plays. We often find that our conversations about science help shift and raise the dramatic stakes of the play. This year, we connected playwright Amy Berryman with Lenka Novak in environmental science and engineering. As Amy and Lenka talked, Amy decided to deepen the complexity of the climate change conversation in the play by having the characters probe into the science and ethics of geoengineering. So to introduce the speakers and the topic of today's discussion, I'm going to read a few lines of the play, The New Galileos by Amy Berryman. One character, Nora, has written a proposal to the National Science Foundation on geoengineering research, while another character, Beth, scoffs at her research, claiming that it's more worthy of an Elon Musk kind of a grant instead of the NSF. Nora thinks that geoengineering doesn't solve the problem of ocean acidification enough. But the third character, Elaine, is fascinated, especially, she says, by the idea of solar radiation management. She says, spray sulfur dioxide high into the stratosphere, which would then be converted into aerosol and reflect the sun's radiation back into space and cool the planet. Sort of like the effect of a volcanic eruption. But Beth counters that we have no idea what kind of impact any large-scale manipulation would have on people, on the land, on indigenous peoples, on ecosystems. She argues, the planet cools. What happens when we stop? It would warm back up like that, and it would harm the smallest communities on the planet, and probably us too, but they're the ones who'd be sacrificed. So to talk about the technologies of geoengineering, solar radiation management, and climate change modeling, and to explore the ethical and social questions of these technologies, let me introduce you to our panelists. Paul Wenberg is the R. Stanton Avery Professor of Atmospheric Chemistry and Environmental Science and Engineering, and he is the director of the Ronald and Maxine Lind Center for Global Environmental Science. Professor Wenberg's research group has played a key role in the development of remote sensing of greenhouse gases from space. They helped create the Total Carbon Column Observing Network to measure the distribution of greenhouse gases across the globe. Paul was also a contributor to a recent study by the National Academies of Science, Engineering, and Medicine, which recommends the US conduct solar geoengineering research over the next 5 years in cooperation with other countries in order to determine whether or not the technology should be on the table as a potential way to avert catastrophic climate change. Jess Adkins is the Smits Family Professor of Geochemistry and Global Environmental Science. Professor Adkins is a geochemist, a chemical oceanographer, and a paleoclimatologist who works on projects to better understand the mechanisms of rapid climate change and climate evolution. Much of his current work is centered around the geochemical investigation of past climates and the rate of deep ocean circulation and its relation to mechanisms of rapid climate changes. And finally, Lenka Novak is a postdoctoral scholar, research associate in environmental science and engineering. She is currently working on developing a new generation of computer modeling that uses machine learning to build computer simulations of what will happen with climate change. Her group's computer simulations will be able to model different scenarios and representations of physical laws that change under various conditions, such as climate change or solar radiation and geoengineering. The modeling will be able to determine the global and long-term effects from geoengineering interventions. And I'm sorry to say that our playwright, Amy Berryman, was not able to join us today. She is currently in London on the West End, working on rehearsals for a play that's going to open there, a new play called Walden. So I am going to turn now to our panelists and ask them to talk for a few minutes about their research. So let's go in the order that I introduced you, Paul, then Jess and Lenka. And then we will have a period of time when I will pose questions to our panelists. And panelists, please feel free to talk to each other and ask each other questions as if we're all having a conversation with each other. And then audience, after that, we'll have a time for you to ask your questions. At any time, you can put questions in the chat and we will do our best to get to them. So, panelists, would you please introduce yourselves and your work by telling us what is one of the most exciting things you are doing right now in relation to geoengineering and climate change? Paul, can you get us started?
Yes, for sure, Arden, and thank you very much for the introduction. I need to start out by saying that I do exactly zero research on geoengineering right now. I have been involved in the conversation around these technologies, and I'm very excited to share my perspective today. But in terms of the research that's going on in my own lab, we work on several different problems, one of which directly relates to the carbon cycle on Earth. We're trying to understand if we can quantify the emissions of CO2 from all the nations of the world. As you know, and as you heard in the last week, nations are making very strong commitments to reduce their CO2 emissions. And this is, of course, really wonderful. But it also begs the question of who gets to monitor those changes. Do we have a way of understanding whether nations are living up to their commitments? And so one of the things that we've pioneered in my group and in collaboration with others at JPL is the ability to do remote sensing of greenhouse gas in the atmosphere, and thereby to try to understand how emissions are changing. I've also been working on the natural carbon cycle, so trying to understand in particular how the forests are responding to the changing climate. And so one of the recent studies from our group looked at the high latitude forests. These are the forests that exist across Asia and North America, and how they're changing as the temperatures warm. And so those are the key things that are going on in my group around the question of global warming.
Thank you. Jess?
Thanks so much, Arden, and thank you for bringing us all together. This is going to be fun hour and a half. I'm really looking forward to it. And it was also fun to participate a little bit in the development of the play over the last 6 months. That was a really special to listen in on some rehearsals and then offer notes about the science part. It was fun to see that last night kind of culminate. Mm-hmm. Though I have to admit, I missed a chunk of it because it was also my son's second basketball game in the last year and a half. And we've been jonesing for a chance to watch little joy flow out of him. So I did go over to that towards the end. I am actually have a research front open on what you might call geoengineering, or trying to do negative emissions technologies, take CO2 and lower it in the atmosphere. It grew out, of course, because this is just the way Caltech works, it grew out of the basic research that we were chasing down. And I have, for most of my career, wondered why atmospheric CO2 goes up and down naturally in concert with the glacial cycles. And that has gotten us interested in how the ocean and the atmosphere partition carbon. And in studying that, and in studying the dissolution rate of the mineral calcium carbonate, that's what coral shells, coral skeletons are made out of, the shells that you find on the beach, mostly as a way to think about the other CO2 problem, which is ocean acidification. We realized that we might be able to engineer a version of the natural reaction that will happen to buffer all the atmospheric CO2. That is called the accelerated weathering of limestone, or AWL, as you get into techno speak and try to make up things so people don't understand what you're talking about. That's a real goal of scientists. The accelerated weathering of limestone is mimicking the reaction that we know will buffer atmospheric CO2 because it's been going on for billions of years. And that is excess CO2, say from volcanoes, or in our case, burning of fossil fuels, will make its way into the surface ocean. It'll make its way into the deep ocean via the overturning circulation, and in there be buffered. The acid of the CO2 will react with the base of the calcium carbonate at the bottom of the ocean to neutralize the CO2 and turn it into bicarbonate salt. It's exactly like taking an antacid when if you have an upset stomach. It's the same chemistry. We are thinking of ways to accelerate that process, and we have begun to target the shipping industry because we think that we can help the shipping industry reduce their emissions to maybe even zero while they're underway by carrying limestone along with them and running a reaction that we're designing the reactor for. And that would be 3% of global emissions right there, turned into bicarbonate ions in the ocean. And so I'm sure that's something that we can dig into a little bit because it raises all sorts of fun technical and unknown science and therefore ethical questions about what to do, what should be done, is there an order thing should be done. I'll just say that I've had my own personal arc of this over time, right? That when I first started hearing about geoengineering, I was very much like, there's pretty much no system we can't interfere with that we don't mess up worse as humans. And I have more and more, and maybe it's because I have a dog in the fight, but more and more come around to, boy, the clock is ticking, right? We are really like, if we don't do anything, the cost of not doing anything is actually quite high. And so it'd be fun to get into questions like that in the panel too.
That is very exciting and interesting. Thank you so much, Jess. And thank you for your involvement with the play and with all the plays we've been doing over the last couple of years. You've been involved before. It's been very exciting to have this.
Yeah, Caltech Theater, go.
I know, this art science collaboration has been wonderful. And Paul too has been involved in the past. Lenka, can you tell us what's exciting about your project?
Hi everyone, thank you so much for having me. It's also been amazing getting involved in the play. It's got me thinking about some of the kind of issues that I'm dealing with right now, not in terms of just work, but also the sort of personal kind of drama, not drama, but the kind of, when you're torn between different issues of life. So that was very rewarding in many ways. But my work is working with Tapio Schneider's team called Klima. And we are a group developing a new climate model from scratch. And this is very much needed because climate modeling is really at the center of kind of information to the geoengineering research, because it gives information on when and how urgently it's going to be needed. That's one aspect of it, and the other aspect is how does the climate respond to your intervention, or whatever the geoengineering method might be. So right now, the kind of classical climate models that are being used, there are tens of research or climate modeling groups who are trying to make their best predictions for the next 50, 100 years. And the problem is that these models vary in their response. So they all agree that we will be continuing to see more warming in the future. But the amount of that warming, the global warming, differs in these models. It differs between 2 to 6 degrees per doubling the amount of CO2. So that's huge. That means that, for example, the Paris Agreement, where we were, countries were committed to try to reduce their carbon emissions so that we didn't reach the 2 degrees above the pre-industrial levels. The amount that the models differ can make a difference whether we should be acting in the next, or we should be reaching this threshold by the next 10 years or the next, 50 years. So so the amount of urgency for geoengineering is determined by how well he can predict. And so our group is developing this brand new climate model, which is supposed to put some kind of new values to the uncertainty of these predictions, which hasn't been done before. So we are using some machine learning methods, which will give us an idea of the uncertainty of these predictions. So that's kind of the innovative bit about our project and our contribution to geoengineering.
Thank you. Panelists, this is going to be an exciting conversation. There's so much already on the table. Let's begin by talking about a recent project that was canceled in Sweden, and then definitely get to this, the accelerated weathering of limestone. That is so exciting. So in March of this year, the National Academies of Sciences, Engineering, and Medicine recommended that the US invest $100 to $200 million in solo geoengineering research over the next 5 years. But then just a few weeks later, the New York Times published an article announcing the cancellation of a test flight that had been planned for June in Sweden. That project is called SCOPEX, led by scientists at Harvard University. SCOPEX researchers are trying to better understand the proposals of injecting substances into the air to reflect some of the sun's rays back to space, and thus reduce global warming relatively quickly, which is what we just heard from the play. But Nicholas Hallström of What Next, an environmental research group based in Sweden, said of the protests about SCOPEX, the mobilization against this project in Sweden has been remarkable, uniting scientists, civil society, and the Sami people against the danger of a slippery slope toward normalization of a technology that is too dangerous to ever be deployed. So Paul, and maybe just you, can you get us started by talking about stratospheric aerosol injection, like the SCOPEX project? And then later, let's get to understanding this slippery slope that protesters are concerned about.
Yeah, it's fascinating. Sociology mixed with politics, mixed with science, and it all comes together in a unique way when we think about the types of technologies that we're describing today. And it was a very interesting thing for me to be involved with the National Academy study, and I learned a lot. You know, as natural scientists, many of us really don't appreciate the larger social domain in which policy and research around climate is coming together. And so the panel included a number of ethicists, philosophers, and lawyers. And so I learned a lot about understanding of how these social contexts of research will play a big role in indeed in how you can actually do research, which is interesting. And so let's talk about first a little bit about the technologies. And so I want to make an important distinction here between carbon dioxide removal, the kind of work that Jess is doing right now, and solar radiation management. So when we, you know, one sort of analogy I would put to this is you know, you have you're uncomfortable because your window's open and there's a terrible smell because there's garbage outside. And solar radiation management is going out there and spraying some odorant on top of it to try to mask the worst of the smell. And the work that Jess is talking about, carbon dioxide removal, is literally cleaning the garbage. And so I think, you know, we need to really think about this. And this is one of the reasons why solar radiation management is such a difficult conversation to have, is because it does, just as the play and Amy point out, it is potentially a way in which we could prevent the Earth from warming. At the same time, it does not do anything to address the underlying forcing that is producing the climate change. In other words, the CO2 would continue to accumulate. Oceans would continue to become more acidic. But what this technology could do potentially is to prevent the surface temperature from warming as fast as it would otherwise. And so most of the conversation, I'd say all of the conversation around solar radiation management is not as a solution to global warming at all, but rather a way in which you might mitigate the worst effects at the peak of the heating. And in fact, if you did solar radiation management, the importance of mitigating greenhouse gases becomes even more clear, because as Amy points out in the play, if you were to stop doing it, you would turn the heat on really fast. You know, within a decade, you get the entire amount of warming that you would have had absent doing anything. And so there's a real tragedy at the end of this, where you did solar radiation management masking the pollution, and all of a sudden, for some reason, you stopped and you cooked the planet. And so there's really these technologies are the solar radiation management technologies in particular have this aspect of masking. And that leads to the next question, the one that you asked about the so-called slippery slope moral hazard. And here the argument goes something like, if we even research technologies like this, it will lead us to a false sense of progress in a way that prevents us from doing the necessary work of rapidly decarbonizing our global economy. And one thing I learned being on the Academy study is that while that makes a lot of sense when you say it, there's actually very little evidence that that is true. These arguments around slippery slope and it cuts both ways. When scientists say, boy, we really need to consider these kind of ideas, it actually can raise an alarm. You know, are you really thinking that this is something we might have to do? Are you really that worried? And so these arguments around slippery slope and moral hazard turn out to not have a lot of scientific evidence behind them. Clearly, we need to think about that and understand how these interactions between what we study and what the world does. That's an important thing to think through. But the simple argument that if you do it, people will be less likely to act towards mitigating greenhouse gases or other things like this, it really doesn't have, there's not a lot of evidence that actually that kind of process happens. And so I would say, you know, as a natural scientist and thinking about approaches towards really potentially mitigating the worst effects of global warming, we'd be foolish not to at least consider and do some research. You know, the research is as likely to be disabling as it is to be enabling of these approaches. But right now, despite what people will tell you, we simply don't have information about what the direct and indirect effects of deploying these kind of technologies are.
And Paul, can I add one thing to, I think it's fascinating your point that you learned while on the panel that the slippery slope arguments that sound so logical turn out not to be true, or at least this aspect of them. There's also something, and we've talked about this before, very specific about SO2 injection to the atmosphere, in that it's cheap. And it's actually, a wealthy individual could go do it right now. And so we're putting blinders on, right, to that very real possibility if we say, and we don't want to try to understand the consequences before it happens.
That's so true, Jess. I mean, one of the things that is directly described in the report is that there is this lone actor potential for and particularly for the SO2 injection in the stratosphere, a modestly wealthy country, or as Jess says, a very wealthy person would have the resources to do this. And so we it seems like that makes it even more compelling to understand what the potential is, even if you would never think about doing anything like this bilaterally.
It sounds a little bit like the Scopex protests and the cancellation of the project there. And I don't mean to sound cynical about this, but really sounds like it was a matter of marketing to the public, that they didn't understand what was happening with the test, that nothing was actually being sprayed at the moment. Can you talk about that a little bit, about this social context of your research? I mean, I don't want it to sound like, yeah, we just have to market it to the public, right? But in some ways, the public needs to understand more about the science. So can you sort of talk about that a little bit more?
And actually, that's one of the things that's really the major point of the Academy study that I worked on, which is that as much as you think that, okay, we're going to do some research, we're going to go out and we're going to do stuff, we're natural scientists, we'll get whatever permits we need to do this. This is an area where engagement with civil society, as it's called, is just critical. And in fact, one of the whole reasons for the Academy report was that up until now, a lot of the research in these technologies has been done pretty ad hoc. It's been done by individuals funded through philanthropy primarily, and so it does not have the same oversight that we might imagine if it were a national program. The other thing that I should say is that while I don't fully know the details of the Scopex experiment and how they did engage previously, they have made a good faith effort to bring in research governance. They have a board that has spent a lot of time thinking about this, because everyone understood that this was a risk. But to see it play out, in the front page of the New York Times just after our report came out, I think once again illustrates the complexities of research in this domain. In fact, the Academy report makes a very strong claim, which is there should be no outdoor experiments where you release stuff unless there's a good, compelling reason to do it. Just for this reason, we should do the experiments in the lab. We should do the experiments in model world. And we should do experiments in the field, particularly to understand how the interactions of particles and the environment work. And many of those can be done without actually adding anything. You can go study rocket plumes. You can understand volcanoes, as was mentioned. You can understand, you can go study the emissions from ships into the clouds in the marine boundary layer, another technology that's being described. We can understand how aircraft are changing cirrus in the upper troposphere, another technology that's being described as potentially useful.
Lenka, just to kind of follow up on what Paul is talking about right now, another form of this geoengineering is this marine cloud brightening that, as Paul mentioned, is inspired by ship tracks. So ship emissions seed the formation of clouds of highly concentrated, very reflective sulfur aerosols, and those bright formations can be seen from space. But today's climate models don't have the spatial resolution to accurately predict the effects of these relatively small formations. So could you talk a little bit more, Lenka, about your climate modeling programming and how it could help assess forms of geoengineering like marine cloud brightening or cloud manipulation?
Sure. Yes. So this is a very active area of research to make sure that our climate models are representing clouds accurately. The problem with clouds is that it only takes a small amount of the amount of clouds, the amount of water that's in clouds is actually a very tiny fraction. So if you were to take the fun statistic that if you were to take all of the water in clouds and precipitate it on the Earth's surface, you would get 0.1 millimeters of depth of that tiny pond. So there's really a tiny amount, but this amount, when it appears in clouds, these clouds are highly reflective, especially these marine boundary layer clouds, which are these blankets, huge blankets of clouds that form in the kind of subtropical latitudes. So, for example, today we're seeing a very murky weather. It's very murky outside, and this is because this layer of marine clouds is coming from the sea over LA. And if you were to look at a satellite picture, these clouds are very thin, but also very wide in space. So it doesn't matter how deep they are, if they are reflective, then they are very important for the radiation. Because it doesn't take that much, that much water to have the clouds there, but we don't fully understand the way these clouds form as opposed to different types of clouds. We need more research in this area. And that's also the reason why the existing climate models, they differ vastly in the way they represent these clouds. It's actually been found that clouds, especially this type of clouds, is the largest source of error or uncertainty in our climate predictions. So my team is currently developing approximations to how these clouds could develop. And like I mentioned earlier, there are machine learning methods which can make your approximation to the cloud formation more specific to the location on the globe. So you can use very high resolution simulations, which are normally too expensive to run globally. But using machine learning methods, the algorithms can learn from these very high resolution simulations and inform the global climate model, and therefore make the approximation of cloud formation more accurate. And therefore, the cloud formation would be acting in a more realistic way within such model. And once we know how these clouds form and how they affect the general circulation, then we will be able to kind of assess more accurately the effect of geoengineering. So there are two parts of it. One is to understand when and how these clouds form, and the other part is how these clouds actually affect the climate. So, yeah.
Maybe I could comment a little bit about what Linka mentioned as well, and that is, so in terms of solar radiation management, as it's called, there's really strong evidence that if you dump a lot of sulfur dioxide into the stratosphere, that you can, at least for a short term, cool the Earth. The evidence there comes from volcanoes. But the evidence around the marine cloud brightening technologies is actually quite weak. We do see times when ships produce a brightening of the marine clouds, as you mentioned, Arden. But other times when that doesn't happen, and at the moment, as Lenka mentions, really the combination of the large-scale physics, the small-scale physics, the microphysics of aerosols, and this is a tremendously uncertain area. And in fact, it is really one of the key uncertainties that Lenka and her team are working on. And so the Academy report describes research in particular to identify and understand whether or not and how aerosols influence cloudiness in the marine setting. And such research, while it might be helpful to understand whether you could in fact brighten clouds in the marine boundary layer and whether you could have enough of an effect to make a difference, that type of research is really essential for moving the whole climate modeling effort forward, because it really does serve the type of research that we identified in the report would serve to improve our representation of these clouds in climate models.
There's one more point also about the marine clouds, and that's the fact that they are very, very sensitive to the temperature structure of the atmosphere. And there has been some research done on their formation, and that would also include their maintenance using these geoengineering techniques. And it's been found that if you keep increasing the amount of CO2, then you will you can get to a point where these clouds will break up. And what these clouds need for their formation and maintenance is this sort of circulation where their cloud top cools, and then they create this circulation so that when the air at the cloud top cools, it sinks down to the kind of towards the sea, where it collects moisture and goes back up, and that's how they get moisture and how they keep maintaining themselves. But if we weaken this circulation, for example, by having a warmer climate, or somehow we get it slightly wrong with the geoengineering, then we could just get rid of these clouds altogether. And the problem with this is that to get these to get back to the regime where you can get formation of these clouds, you would have to reduce your CO2 well beyond the current levels. So it's like a hysteresis, where if you increase it a little bit, you lose the clouds. You cause a huge amount of warming. And then to get back to where you were right now, you have to go even lower in terms of the CO2 emissions or the CO2 concentration. So it's one of those climate tipping points. So yeah, so without knowing what's going on, it's quite dangerous to be playing with something that could change dramatically, and it's not easily reversible.
Arden, if I could, it's a really great point that Lenka's making about the nonlinearity of climate and how it has to be part of the discussion of geoengineering and what to try and what not to try. Just to chime in with my paleoclimate hat on, one of the frustrating things about studying the history of the Earth's climate is that there is no time that we can just go read the rock record correctly and say, oh, look, this is when putting all the CO2 into the atmosphere very quickly with this kind of background climate happened before, and the Earth system responded this way. There's no version of the tape recorder that we can play that's going to help us that's going to be the actual answer. And so you have to look to paleoclimate more for the basic physics and chemistry and biology interactions of the system. And the main lesson there is that things are very nonlinear, that there are these tipping points and they go off quite dramatically in the ice core records. You can see these things called Dansgaard-Oshkosh events and Heinrich events. And then the climate system stays stuck for hundreds to thousands of years in a state and then flips back. I'm sorry, they're painting outside of our house, so they just turned on a sander, so I'll mute myself here in a second. But just putting that paleoclimate hat on, this point about nonlinearity has to be forefront in our conversation about geoengineering, both of ways that we can make it go wrong, and in this time pressure, right? To figure out, because we are forcing the system in a way we haven't done before with the CO2. Paul, I might flip that back as a question to you just quickly. You talked about how we came up with the right order on the panel, that like, let's do a bunch of things inside before outside. How much of a conversation was there about, and will that slow us down so much that we'll miss the opportunity to lop off the top of the warming with albedo management?
So Jess, I think what you're asking is something that might be sort of captured under the question of urgency, and I have to say it was an area where the panel had very diverse views about this, and I think it just again reflects the sort of just a general cautiousness of everyone in terms of understanding that we need to carefully get to the answer. I think one of the things about doing outdoors experiments is that, as we saw with the Scopex, you have to have a really good reason that you'd want to do them, without which you can't know what it is you're trying to get at. And the reason is simply because those types of experiments are naturally controversial, and they can really set back a whole program. And so while we do suggest that small outdoor experiments might be needed, and particularly in the context of the marine cloud question, where I think manipulative experiments could be done incredibly safely, and you would learn a lot. In terms of larger scale and like the stratospheric ones, you really have to have a good reason to do those. I think otherwise you do just risk having your research set back through the type of events that happened in Sweden this year. But there is an urgency. Just to give everyone, just to remind everyone, we're on a trajectory right now that's pretty bad. The Earth is warming quite quickly. We've baked in 20 more years really of increasing temperatures, and so there really is an urgency, and that urgency I do believe should be reflected everywhere. It should be reflected in how quickly we move towards decarbonization. It should be reflected in our research on all avenues of improving the ability to reduce our carbon emissions, and potentially to bury them the way Jess is thinking about doing, or if necessary, methods we might have for shaving off the worst of the heat if it came to be critical to do so.
Paul and Jess and Lanka as well. To just piggyback on this idea of the urgency of it, do you have a sort of a limit in your mind of unacceptably large risks and costs on vulnerable people that you would be willing, that you need to stop at, that you would not be willing to take? I mean, are there risks that you are willing to take in order to solve the problem of urgency? And are there some that are just too far that you would not recommend taking?
The thing that I think your comment is excellent to think about the risks, and the risks of climate change are to individuals through inequity. So if you look at a place like Bangladesh, you look at a number of countries with the population at very, very low level, close to the water. The risks are very much not distributed equally in this world. And they're often distributed in a way that those with the least resources to adapt are likely to feel the worst effects of climate change. And so I do think there's, when you say risks and benefits, this is one of the really interesting and almost unanswerable question, because these are global risks, but they are quite distributed differently, as I mentioned. And the benefits, of course, also accrue differently. And so, you hear these comments like, who gets to control the thermostat if you were to do solar radiation management? And these are awesome questions, and one which there's no easy answer to. But I do think when you hear from some skeptics who suggest that we shouldn't even do research in this area, I don't think they fully have appreciated just how much risk we face for people who don't have a lot of resources to adapt to a much warmer future.
In the Sweden case in particular, why specifically were the protesters concerned about the indigenous Sami people?
Well, I don't actually know, but one thing I will say is that the location, I've actually been to northern Sweden doing research from where the experiment was intended to be launched. And this is in Kiruna, or outside of Kiruna, Sweden, which is the very far north of Sweden. And it is in Lapland. And so the Sami people, that's their home. And so I suspect that when they bring in the Sami community, they're really talking about, it's like people who are living under the balloon where what they were going to launch. But again, I'm speaking out of just inference.
Arden, can I pick up on a piece of that? It isn't. I'm happy to go back to risk, but this is a little bit touching back on the slippery slope question that was asked before, and we were talking about the need. There's a real question of social and political license to do any of the things that we're talking about. And you brought up that sometimes it feels like we just need to be better marketers, right? And I think there's a part of that that's just true, that we do have to do a better job of explaining what it is that we're doing, or you could even use the word selling what it is that we're doing. But I would say it actually is deeper than that. Like by involving people who it's often just phrased as stakeholders, but it's easy to start saying there are lots of stakeholders in Bangladesh for an experiment you might be doing in Sweden. But to involve people that aren't scientists in the decision-making process from the very beginning isn't just a better way to get to do the thing that you want to do. It's a way to do something better, right, than what you had already thought of doing, right? I think that there is a real back and forth that we kind of miss in the way that we phrase this sometimes as scientists, that, oh, we have to market better from the beginning so that we can actually carry out our work. If you're really being open to it, it's going to change the work that you do, probably in a positive way, and certainly not in a way that you would have predicted from the very beginning. You have your best shot. You think you understood what experiment you want to do because of a model you have ahead of time and some data you collect already. And then involve outside people, crowdsourcing a problem. It's a little like the technicality of the technical part of what Lenka is doing with the machine learning, right? The more folks you get in the room, often the result is better.
I love hearing about this collaborative nature of your research. Maybe that's why Jess and Paul and Lenka, we've enjoyed working with you in the theater so much, which is such a collaborative medium as well. That's really exciting to hear you speak about that, Jess. And just to follow up on that a little bit and to add something else too that Lenka and I were talking about yesterday, we were thinking about climate denialism and skepticism, and the skepticism that many people feel about scientists. And so and along with this idea of more social research and involving more stakeholders, it seems like some of the concern that citizens feel has to do with a different messaging that they're hearing from scientists about this urgent nature of global warming. Some scientists are saying, well, maybe 20 years, or as Lenka was saying earlier, maybe 50 years, and we need better climate modeling to be able to figure out, well, just how bad is it? How do we talk about these various areas of skepticism that some argue is because scientists won't come down with a definitive answer?
Shall I go, or would someone?
Go ahead, Lenka.
Okay. Well, I think when it comes to skepticism, like there is some. So usually when people say, "Oh, climate skeptic," okay, people imagine someone who just doesn't want to hear anything about climate change, and but there are people who question the details of it, which I guess is justified, because even we, like I already said, we have so many very good complex models, but each of them differ in in the way they predict the climate is sensitive to carbon dioxide. So I understand why people are kind of hesitant to make very important financial and kind of life decisions based on these predictions, which is why it is so important to be able to give people more information on these predictions. How accurate is it? How accurate is it? that if you have a prediction that your house will flood in the next 20 years, is it 50%, 60%, or is it 98%? You will probably make different decisions if you have that sort of uncertainty information. And right now we don't have that. So the kind of idea of the current climate modeling efforts, not just my team, but there are many teams who are currently thinking about this, is to make climate prediction a bit more like weather forecasting, where you get a map and you get some sort of amount of certainty behind your predictions, and where it's coming from. Maybe in a particular region, the jet stream seems to be particularly, it fluctuates a lot, so it's difficult to know exactly what it's going to do, but in some places it might be more certain. So yes, so I think that would definitely decrease the amount of the justified climate skepticism, I think. And also education. I think you can have the best prediction in the world, but if people don't know how to read the prediction, then or even how science works, we can't give black and white answers most of the time. But yes, climate change is not the only problem which has that. It's all science can't give you 100% answer. So you have to work with kind of more percentages, and at least in this sort of scope.
I would certainly just riff on what Lenka is saying there and totally agree. I mean, leadership is making decisions with uncertain information, and climate is a great example of that. And that's absolutely what we're going to have to do. Hopefully, Lenka and Klima are successful, and we actually get error bars, right, that really help, because these are not decisions that are made because we know it's going to do this or we know it's going to do that. They're made because there's a range of possibilities that we're wondering about. In terms of denialism, I think to some degree we're relitigating something that's already been decided, and that is COP21, this meeting in Paris, right? The sort of infamous meeting in Paris back when the US was actually still in the Accord, did something truly amazing in the first 24 hours of the meeting. And that was, everybody was in such a rush to get to the bargaining table to try to cut the best deal for their economy, about limit somebody else more so that I can burn more fossil fuel and therefore my economy will do better. They had to decide the rules of the playing ground, right, in order to have that bargaining table. And so they agreed that 2 degrees was dangerous. And they defined what they meant by dangerous. They kind of wanted to do 1.5 degrees, but they said 2 instead. And that political decision has been made. And so we don't have to renegotiate like denialism necessarily, right? If we're willing to move forward, right, with that already made political decision, it immediately means a couple of things about geoengineering. We absolutely have to limit emissions. It's the only long-term solution. We have to make the transition off of fossil fuels into alternative energy. There's just no doubt about it. There's also no scenario of doing that keeps us below 2 degrees. We have to then also think about something that could get labeled geoengineering. You have to think about negative emission technologies, or nets, it's getting sometimes called. You have to wonder if we need to lop the top off the warming because of something so dangerous. The modeling that Lenka is talking about might really be able to help us with that in the error bars. But climate denialism, I don't know, that's kind of yesterday's conversation. Like, we already have a plan to move forward on, and it absolutely requires thinking about technologies to remove CO2 and to think about intervention.
I would totally agree with Jess, and I think he brings up this point that's important, which is because we live in the US, it's easy to have a US centric view on this, but this conversation around denialism and so forth really seems to be focused in the US. There are a few other countries in the world where you have any major political party who has decided that it's in their best interest to try to bury the carbon problem by putting their head in the ground. And so I think the United States is really somewhat of an outlier right now in terms of the conversations that you hear. And as we mentioned at the very beginning, the climate problem is a global problem. And the good thing is that that conversation around skepticism and denialism is really waning fast. That's not to say that there aren't, as Lenka mentions, a lot of uncertainties and that are important, because you have to understand how quickly do you need to act, and what the risks are in various scenarios. And one of the key things there, of course, is that the lack of high quality projections. If you were in an insurance world, which we all are at some level, will tend to make you overreact, not underreact. You hear these comments that we don't know the answer and therefore we don't know what to do. And of course, that's not at all the way the real world works. If you don't know the answer, you realize that the risks are real and present, you tend to waste resources. And so I think as Jess is mentioning and Lenka mentioning, there's just a lot of opportunity here to try to think through the whole risk management problem associated with climate. And the conversation today is around one particular aspect of that.
Thank you for that reminder about the US being sort of an outlier in this climate denialism. That's important for us to remember as we think about this as a global problem and not just US centered. I want to leave time at the end. We only have about 20 minutes or left, but I want to make sure we get to questions from the audience. So please, audience members, throw some questions in the chat if we haven't gotten to them yet. And I want to ask one more question to Jess. Maybe it's because I just think that all of your deep sea expeditions have been super exciting, but I'm really curious to know more about this accelerated weathering of limestone. Paul was talking about the masking of aerosol injections and your work at sort of cleaning up. So could you talk about this some more? It's very interesting.
Yeah, you have to be careful in asking a question like that, because what else do academics like but talking about themselves, right? And so I'll try to keep it brief and not just keep riffing and riffing, but which is both Paul and Lenka know is hard for me. Where to start? I would say that I have gone from thinking about this as like a very general thing of wow, we know what reaction is going to happen. It's CO2 plus calcium carbonate goes to 2 bicarbonates and a calcium ion. There, we just said some chemistry in this discussion, and that's like totally uncontroversial, right? That is what is going to happen, and we know that that is naturally going to happen on a time scale that's quite short geologically, but doesn't really matter for the tragedy of the commons that we're currently experiencing with CO2. And so it's sort of a natural thing to then say, all right, well then if what we're doing with burning of fossil fuels is just accelerating the weathering of organic carbon, that's what a geochemist would call it, we know what the geochemical response to that is, right? It's limestone getting dissolved. And so let's just match one rate for the other, and we'll be following the exact same pathway that the planet is doing. And that's how I have talked about this and talked about it in the earlier days when we were thinking about it. But we've become much more focused on a very particular industry and a very particular problem. And that's because of a marriage of some of all the things that we're talking about here. And there's to help answer a question, this sort of helps answer a piece of a question that's in the chat right now about what % of carbon sequestration can we look to achieve from different practices? Like, what does the pie chart look like? Of course, I'm going to say it depends, and that's not a very fair answer, but let me give you a specific part of it, right? There are pieces of the economy that decarbonize well by switching to alternative energies. Teslas are a great example. right? If we were making clean electricity, then it's fantastic having all these electric cars. Shipping, airline travel, right, are not easily decarbonizable, right? They are really, the fossil fuels are an amazing thing in their energy density, right? And their ability to allow airplanes to fly such long distances and allow ships to so cheaply carry cargo around. And so the kind of approach that you think about for decarbonizing different sectors, the pie chart that I think the person is asking a question about, it depends on the industry. And we're focused on shipping because we think our process marries well to it, because we need seawater and we need limestone and we need CO2. Well, ships burn bunker C, they're floating on the ocean, and they're the largest vessels around to carry anything, you know, and so they can carry tons of limestone. And they match up sort of nicely technologically that way. The industry is also under a lot of pressure to decarbonize through regulation, through what's called IMO 2050. That they have to have 50% of 2008 emissions by 2050, and they don't know what to do. And so there is a unique aspect of this geoengineering part that has a real business side to it, right? That is, you often hear about people saying, I'm going to take my process to suck CO2 out of the atmosphere, or pull it from some source, and I'm going to make feedstocks for plastic, or I'm going to sell it to Coca-Cola, or I'm going to sell it to greenhouses, to pure CO2 to greenhouses to grow more plants. That's great at first. Like, you can imagine that you might come out making money and have an economy of carbon sequestration leading to actually new wealth, or, you know, people making money. It doesn't work at scale. It's a totally different issue than the climate problem. And that's because the waste of the fossil fuel industry, right, is the single largest stream that we have. That is the amount of CO2 we burn in order, the energy economy is the largest economy on the planet. And so its waste product can't be taken up by any other piece of the economy. And so there's complete scale separation in this, right? If you're making a product, that's fantastic for getting started. You can't scale, right? If your product relies, if your process relies on making that product in order to keep going. And that's like a tough nut to crack. And what's really kind of neat about the shipping industry is that they land right in between. Like, they're 3% of global emissions, so it's a big number, but they're under this regulatory pressure that they actually need to come up with a way to work on it. And so we've been doing experiments in the lab, and we're beginning to try to build a prototype that would be a reactor that you would carry on a cargo ship that had a fraction of its volume for taking our stuff all around the world, right, taken up by holding limestone instead. And you would plumb the flue gas out of the diesel generator through seawater in the presence of limestone and do this reaction. And then have the seawater come back off the ship. And that is the uncertainty. Like, we're actually very certain about a lot of the technical parts of what I just described. And then what happens with bicarbonate enriched seawater as it comes off the ship, I'm not sure. I know chemically what's going to happen, but I certainly don't know ecologically what's going to happen, right? What if there is a community out there that really likes bicarbonate, right? And so I think I'm sort of answering your question about what we're up to. To put it into themes of this conversation, where we have real uncertainty and we're worried about that, you know, try not to do less harm than the solution to your problem, is in that effluent coming off the ship of what is it that enriched bicarbonate does in the surface of the ocean. We have some good ideas from the chemistry side, but I think there's a lot of work in front of us from the ecology side. I hope that's at least marginally answering your question, Martin.
Yes, that's very, very exciting. And I'm also curious, though, the same sort of question that we asked earlier was, it sounds like very promising technology. It sounds like it's available. It sounds like the shipping industry would be very interested in it. It sounds like it solves a lot of their problems. We don't know yet what some of the ecological risks would be, but would you be willing to move forward with it, not quite knowing exactly what those ecological risks would be, knowing that it does solve these problems immediately that we are in such urgent need of solving?
Our very specific answer to that is to change the order from being very linear. It's a little bit why I was asking Paul this question earlier, right? That it's very obvious how you'd want to go about this in a particular order to know answers from A before you go do B and before you go do C. We feel the time pressure, we feel the urgency, and so we're trying to do them in parallel. We're not trying to forget about any one of the problems, but we're trying to make mistakes on all fronts early so that we can learn. I think you can minimize the risk of the effluent by doing in a way that it's harder with SO2, right? By doing small scale studies, by doing something like, let's go in a patch of the ocean, spray in some calcium bicarbonate and watch what happens. That would be a really useful experiment to do. There are things to do at the lab bench, and I know of a few groups that have started. Our answer to this is work in parallel, not in series.
Thank you.
I was going to comment on the other hard to decarbonize technology that Jess mentioned, that's aircraft. And I can bring it back to the discussion around solar radiation management. And that is, so the idea or the concern here is, if you look at the photograph behind me of Caltech, you see those high clouds up there, and a number of them have these linear streaks, right? And so these are almost certainly initiated by an aircraft passing at high altitude in regions of the higher atmosphere where adding both water and particles can cause a cloud to form. And recent calculations suggest that this, so second of all, those clouds are warming. Those are the clouds, unlike the clouds that Linka was talking about earlier in the marine cloud brightening, the clouds that are high in the atmosphere, like these ones, warm the Earth. And they do so because they're thin, so the sun goes right through them. But if you were to put on infrared glasses and look, you'd see that they're opaque, that they're radiating a lot of heat back at the Earth. And you know that's right, that on nights where you have, that it's very, very clear, the temperatures cool pretty fast. And if you have a night with high clouds, the temperature will drop much more slowly. And so the idea around geoengineering of those clouds was that there's some suggestions, and basically we really don't have any idea if that works. That if you were to spray the right kind of particles up there, you could make those clouds go away. Huge skepticism that this actually works at all. But the other part of this is that we do know that airplanes today cause cloudiness, and in fact, that cloudiness may double the warming impact of aviation. In other words, the CO2 is only half of the problem. The other half is this cloud nucleating properties. And that's something that the type of research that we describe might lead to real answers. You know, we're learning a lot more about when and where these clouds form. We're learning more and more about the way in which those interact with the larger climate system. And you can fly a plane in a different place. So if you know where you're going to cause these clouds to form, in theory, you can drive the planes other places around those regions at higher or lower altitudes. And that's actually an area of active discussion right now, that we could reduce the impact of aviation considerably, not through reduction of the CO2, but through reductions in the clouds. And I think it illustrates once again just how complicated our science is here. You know, you think about CO2 goes up and it warms the surface, but then there's all these other effects that are significant. You know, how does it change the amount of water? How does it change the amount of cloud? And these are the things that we know the least about.
And to also touch base with that idea of how complicated these systems are, I have a question from the audience member that asks about agriculture, which is another thing we haven't talked about. What % of carbon sequestration can we look to achieve from agricultural practices and soil sequestration? Jess, you talked a little bit about that question about the decarbonization, but can we particularly talk about agriculture for a second?
Uh-oh.
I know that's not one of our specialties here.
No,
or is it are you going to start having you have a passionate thing to say about it?
No, I don't. It's not very impassioned at all. I am skeptical of a few parts of the agriculture of use of agriculture, and really it comes down to something that's really is pretty simple, which is that every year it's almost true down to the very to significant figures that photosynthesis equals respiration. And so what we're talking about is the residual from two very large fluxes. And so immediately it becomes hard to count, right? Because very small differences on either one of those fluxes are huge differences in the inventory, right, of what's happened. And it tells you that the biological system is very efficient at getting rid of carbon that it's fixed, right? And so you have to be thinking hard about how you can beat that efficiency. Where I've wondered, I think I might have even asked you this question at one point, Paul. Like, a place I would like to go to, and it'll be a good number to try to understand, is how much carbon has been removed from soils since modern agricultural practices have come on board, because that's probably a good number for what the available storage room is. That's like the size of the container. And a lot of these conversations get caught up in all sorts of modern agriculture tweaks and things that I think miss sort of the point, right? That the first thing that's happened is that modern agriculture has decarbonized soils in a big way, and that's increased atmospheric CO2. I don't think there's a lot of question about that. If we could understand how big that was, that's got to be the starting point for how much room there is to put CO2 back in the soils. My intuition, and I have no real expertise here, so you shouldn't believe my intuition over anybody else really, is that it's not actually that big a number. But Paul, maybe you know better, or Lenka, you've looked at this in the bio side of the modelings. That's how I'd approach the problem in a net sense.
Yeah, I think you're right, Jess. I mean, the key question is what has happened to carbon stocks on land, as a good part to think about what you might restore. And a lot of this is so carbon stocks on land in the Northern Hemisphere are increasing right now, but a lot of that's through afforestation. In other words, environments which were cleared for agriculture and are now regrowing. And if you've been to lots of places in the East Coast in particular, you can just see this, the forests are reclaiming a lot of the land. And I think that brings up the point that in my mind, that is probably the most important, is that agriculture that deforests large landscapes, in particular right now in the tropics, is a real problem. It's not so much that we're saying you can try to manage your agricultural to make them sequester carbon, and there may be some ways to do that. But I think the biggest question right now is what's going to happen to a lot of the remaining tropical forests, and if they are converted over to agriculture, that's going to represent a very large loss of carbon stocks and an increase in atmospheric CO2 as a result.
I can also add from the modeling perspective that land processes, especially soil processes, have not received that much attention in the modeling world. And it's clear that even small amount of progress in improving these models makes a huge amount on the actual prediction. So we are developing as part of this huge, I say climate model, it's really an earth system. So it involves these land and soil processes as well. So we have a component which involves more complex processes, and this will be part of it. The soil processes and the interaction with the biosphere, and how vegetation is affected by the atmosphere. All of those linkages will be considered by this model. But it's only quite relatively recently when people really started to focus on these aspects in climate modeling.
And let me just ask one more question that's in the chat, and then we'll need to wrap it up. I think most of us are teaching a class pretty soon. But this one follows up with this question. Instead of, or in addition to, agricultural sequestering carbon, what about changing what is grown? For example, more plant protein instead of meat. The factory farming industry is a huge problem with carbon emissions.
I haven't looked at these numbers all that recently, but you know, in figuring out your personal carbon footprint, right? Like what could you do, like to change your own actions to help with the global problem? Don't fly is at the top of the list, right? Don't get on airplanes, but a very close second, and you could, is become a vegetarian, right? And so I think it's an excellent question and a good point in the chat there. The amount of farmed land area associated with eating the equivalent number of calories of beef compared to vegetables is just vast. It's just an absolutely huge difference between them.
I also get the impression that it depends where, even if you're vegetarian, the source of your food matters as well. So if it comes from, you know, an organic field where, you know, they haven't removed all of the bacteria, but store all the carbon, that's much better for the climate than some, you know, huge farm, which, you know, like we just said, decarbonates all of the soils. Yeah, so I think it's, yeah, people should definitely look into the source of their food.
It's true too, as the conversion to animal protein is hugely different depending on what animal you're talking about. You know, fish is really incredibly efficient. So if, the amount of food you have to feed the fish to get something for us to eat is way smaller than for other beasts. So that it's not just becoming a vegetarian. You can do, you know, you could become a pescatarian, and that would also help. Of course, the fishing has a whole lot of other environmental issues, and so those have to be considered as well.
Just for full disclosure, Arden, I'm not a vegetarian, and I do enjoy eating meat. One thing that in my own personal journey on this, just to Lenka's point, right, is that I have enjoyed understanding a better connection to my food, its origins and what it is and that's actually just made me enjoy dinner more. Like that, it's just, it's in a sense more fun and more interesting and more flavorful to eat when you start just paying attention to where it comes from. And in our household, we still eat meat. The joke in our household is that I'm going to become a pescatarian, where I only eat fish that eat other fish.
I just watched a film called Kiss the Ground, which is a very exciting film talking about agricultural soil carbon sequestration. So it's on Netflix, very exciting film, and it gives a lot of personal things that you can do in your own journey, in your own daily life, and your career choices that you make about agriculture and about soil. It's really beautiful. Well, speaking of things that are really beautiful, this has been an absolutely wonderful discussion. Thank you so much, everybody. I just appreciate this conversation, and I appreciate your time that you've taken to come and join us, to talk about this subject. It's so important, and I learned so much today too. Very exciting. We're going to put in the chat this, oh, here it is. I see it right now. Register to receive the link to see a free performance of this play that we talked about at the beginning of our discussion, The New Galileos by Amy Berryman. Brian Brophy is the director, and they did a very exciting production of it with the green screens and really advanced technology. Very exciting performance. So please join us with that if you can. There's another performance tonight and another one tomorrow. Everybody, thank you so much for joining us, and I look forward to hearing more about your research.